Hi class, welcome back to electromagnetics. We continue our discussions now, extending Maxwell's equations now that we've developed those back to static fields. And we're even going to take it further today and even look at some circuit elements that hopefully will look familiar to you from previous courses. Inspirational thought for the day from Psalms 46:10. He says, "Be still and know that I am God. I'll be exalted among the nations. I'll be exalted in the earth." Thought this was appropriate since I guess we're talking about static fields. Uh, we have been dealing with varying fields, always in motion. So now the fields are being still or are static. In the same way, God, instructs us to be still and know that He is God. Sometimes we get so busy and so caught up in things that I think we lose perspective. And so this is the instruction in this verse: is, hey, slow down, be still. Remember, I'm God. I'm in control. We'll continue part 6 of the course. This is mini lecture number 3, again, static fields and circuit elements. So we want to continue our discussion from the previous lecture, and there's where we recalled Maxwell's equations in integral form. And so we have Faraday's law, Ampere's law, and then Gauss's law for electric and magnetic fields. So hopefully they're starting to look familiar to you and you're becoming familiar with the variables. So if we now apply the conditions that all the fields are static to Maxwell's equations, same equation as before, this then would imply that any time variation in these equations would be 0, right? Because the fields are static. So right off the bat, we see that our magnetic flux derivative with respect to time and our displacement current derivative with respect to time, those are both going to fall out. So they'll be 0. So making that adjustment, we're left with this. So this is the simplified version of Maxwell's equations in integral form for the special case of static fields. So Maxwell equations for static fields, then we look at these guys. So just to review, these are the tools in our bag at this point. So we've got the integral form. And remember, we've got these equal to 0, and the displacement current's gone here and here. If we do have any current density, it's going to be a constant, and in many cases it will be 0. And then same thing on the differential side. This is set to equal to 0. The displacement current doesn't play a role anymore. And again, if there is current density, again, it'll be constant. So if we examine these equations, a little more closely, we're able to make some fairly significant observations. The first one is that unless the current density includes a component due to conduction current, the equation involving the electric field then are completely independent of those of the magnetic fields. Remember, this was a big deal when we had time varying fields. They were coupled. They were cross coupled, actually. What happened in the current influenced what was going on, or what happened in the electric field is going to influence what happened in the magnetic field, and vice versa. What was happening in the magnetic was affecting what was in the electric field. So they were cross coupled. Static fields, unless there's conduction current, it's not the case. These will be separate. So the source of the static electric field then can be solely attributed to any charge that we have in the area, whereas the source of the static magnetic field is only attributed to any current density we have, and they don't have to be necessarily related. So this is interesting here because according to these equations, then there's no relationship, or could be no relationship, between the two. So the only way that the electric field and the magnetic field can be coupled then is if there is conducting current. So if there's no conducting current and these fields are both present, then the result is called an electromagnetostatic field. So electromagnetostatic field. So let's start to look at some specific situations. So first we're going to consider an example of an electrostatic field by considering an application involving capacitance. So here's our standard setup for a capacitor. So we've got this conducting plate, this dielectric in the middle that's sandwiched between another conducting plate. And so we're going to say that these conducting plates have a conductivity that's infinite, and this middle region, the perfect dielectric, has zero conductivity. So this is, of course, theoretical, and so it will have a permittivity and a permeability associated with it. And so if we look at a side view, you know, as we put a voltage on it, we'll start to see the fields. So like I said, we'll put this voltage V naught across them, connected to both the conducting plates. And this is at Z equals negative L, so over here, so here's your Z axis going this way, and your X axis going up and down. So we want to neglect any fringing of the fields, which you'll see in higher classes of electromagnetics. You could have some fringing around these plates here around this dielectric. This now reduces then to a one-dimensional problem, right? The fields are only going in the X direction. So we don't have to worry about that. So that simplifies things. And so this now looks a little more like what we would expect to see in electrical circuit analysis, which you've had up to this point. And so we want to look at these concepts in terms of through the perspective of Maxwell's equations. So if we do that, we can apply now Poisson or Laplace's equations, and we see that according to these equations, the second derivative of the voltage in the x direction has got to equal to 0 according to these equations. So if we do the math and do the double integrals on this, we're going to come up with an equation for V in terms of x, which will be V naught over d times d minus x. And so you can see then if you apply these in here at x equals to 0, your voltage at the top is V naught. At x equal to d, it's equal to 0, and so it's linearly distributed through this dielectric. So now that we have an expression for V, using these equations again, we can find an expression for the electric field, which is the negative gradient of V. And if we take that and apply that in, we get V naught over d in the x direction. We can also take into account the permittivity of the material, and so we can find the displacement current vector by just multiplying by the permittivity of the electric field. So now we can apply the boundary conditions for the displacement current to determine the charge on either plate. And to do this, we consider this relationship here from Maxwell's equations. So the integral across a surface, the displacement dotted with the value of the surface, the area of the surface, this is equal to the total volume and the charge contained in it. And we've seen from previous lectures that either of these, when it's evaluated, just gives us the total charge Q. So in this case, we can say the total charge Q. In this case, we can take the D vector, which we have an expression for. We know the area of the plate. It's just this width times this length here. So we plug all these values in, multiply everything out, and what we get is it's just the permittivity times the area of the plate divided by the depth, D, times the voltage. But we recall, hopefully from our circuit analysis, if not, you can go back and look in your older textbooks and see that we define capacitance as the charge in the capacitor divided by the voltage across the capacitor, which in this case is equal to the permittivity times omega L over D, which is this equation divided by the voltage. So we should also note that with this arrangement with the capacitor, we now have some stored energy in this capacitor, right, in the form of an electric field. So we've examined this concept in previous lectures. So if we look at that, we recall that the equation for this stored energy is 1/2 times the permittivity times the electric field squared. And this is going to be times this volume, the width times the length times the depth of how much energy stored in the total capacitor. So in this case, we have our expressions for some of these things, and we'll plug those in, rearrange the variables a little bit, and we see that this is the capacitance, the voltage squared, so this reduces down to it's just 1/2 times the capacitance times the voltage squared, and you may remember this as well from circuit analysis. So this is the total energy that can be stored in a capacitor. A couple of notes on this on capacitors. This demonstrates here that capacitors do store electricities. This does store electricity. I want to make clear, I don't want anyone to go out of any of my classes making the claim that batteries store electricity. Batteries do not store electricity. Batteries are a chemical device that has a chemical reaction that produces an electric current or electric voltage. So they store energy, but not in the form of electricity. They do it in the form of chemical compounds. So don't ever be confused about that. The other thing is, because of this, if we were to apply this voltage and get this energy stored on here and then suddenly remove the voltage, that energy is stored in there. So you have to be careful when you're dealing with capacitors. When you come upon one that's sitting on a shelf, you're going to want to short out the leads. You don't want to touch it because it can shock you. And if the capacitance is enough and it's large enough and the wattage is enough, it could do serious damage to you, and it could actually be fatal. So, when I'm in the lab and have bigger capacitors, I usually encourage my students to, when they're done with the capacitor, short it out and then take a wire and wrap across the leads just to keep it shorted out so that you won't have any of this storage for dangerous situations later. So now I want to look at inductance. So to do this, we're going to have a similar setup as before, except on this time, in this case, we have the conducting plates as before, but we're going to wrap around with this other conducting plate. So we're actually coming all the way around the dielectric. So this area in the middle here is dielectric, and this area that goes all the way around is like wrapping it around with a metal plate or something that would be a conductor. So in this case, instead of putting a voltage source, now we're going to put a current source out here. So we'll have a constant current flowing around this plate. Again, we're going to neglect fringing effects, and when we do that, we see that this again will be a one-dimensional problem, at least as far as the fields are concerned, that everything should be going in the x direction and the y direction. So using the current source, the dimensions of the wrapping plate, now we can define a current density, right? So we've got this current density, and it's simply just going to be the total current of the source divided by this width here. And so you'll have it going in the z direction, you'll have it going in the x direction, and you'll have it going back in the negative z direction. And so that's what this is indicating here. So in the current free region, Ampere's law then now becomes this matrix where we just have the partial with respect to x. Remember, y and z have no contribution because it's a one-dimensional problem, so we'll have our magnetic fields and our directions, and so we can just solve for that. And then we have Gauss's law, which will tell us then that the partial with respect to the x direction of the magnetic flux density should equal to 0. So because this is one-dimensional, it's simplifying our math by quite a bit. So because of this, then we can note right away then that our x and z components of our magnetic field, the x and the z, those must be 0 in order to satisfy these boundary conditions, because they are bounded by a perfect conductor. So if we apply these conditions, we now have expressions for the magnetic field and then the flux density vectors as follows. So our magnetic field is just simply the current divided by the width here, so that's our current density in the y direction, and then our flux density, we can relate that by the permeability of the dielectric material, and so we just multiply by the mu constant. So now we apply Faraday's law, and we can relate the flux then with the current as follows. So the flux, which is this phi term here, is equal to the mu I naught omega, which is B, our flux density, times this length, this differential length dl. And so we can rearrange that in this case to see that it's this constant times the current. So bringing that forward, we recall from circuit analysis then that the inductance for an inductor is defined as the total flux over the current. Well, we have our expression here for the total flux. We divide it by the current I naught, and we see we get this mu times the distance times the length divided by the width of our device here. So this is how they determine these values from the physical properties of the devices themselves using Maxwell's equations. Again, we should also note that with this arrangement, we now have stored energy in the inductor as well, in the form of magnetic field energy between the plates. And so we go back to our equation here with the magnetic field in play, and it's again times the volume of the device. And so when we plug in the values we have for this and rearrange them, we find that it's just 1/2 times the inductance times the total current squared. And so, unlike capacitors, this is not going to be dangerous from sitting on the shelf because this energy is only stored when there is actual current flow. So when it's sitting on the shelf and there's no source tied to it, you're not going to have the current flow, so the energy is not stored in there, which this is unlike or different from the capacitor, where it will still store the energy even when the voltage source is removed, because you still have that potential difference between the plates. So just a big difference there. And why? Finally, we want to consider example of the electromagnetostatic field by considering an application involving conductance, and so this will relate to resistance. So to do this, we're now going to consider the original configuration that we had before with the capacitor, but this case we don't have a perfect dielectric. We'll have an imperfect dielectric, which means there will be some current flow between the two plates, whereas with the capacitor we assume there was none. So as before, we're going to put a voltage source across the plates, connecting at Z equal minus L. And now we again want to neglect the fringing due to the fields. And when we do, again, this reduces to a one-dimensional problem, just like the other two, which gets us back to what we're used to seeing in electrical circuit analysis. So as before, this electric field then is given by this equation where we take the divergence of the voltage, so V naught over D, which in this case leads to the definition of current density in the dielectric. And so the current density here is just the conductivity times the voltage over the distance that we're displacing those two plates. So bringing this forward, the current through the device then can be expressed as this current density times, this conductivity times the voltage over D times the width times the length. And so we get this resulting equation. We now recall the definition for conductance from circuits class, which it's the current over the voltage, which is the opposite of resistance. So it's just they're reciprocals of one another. But in this case, if we plug these in, we get it's the conductivity times the area of the plate divided by the displacement. And like I said, this is same as resistance basically, where we just flip everything here. So as before, where there is no opportunity for energy storage per se in this case, there's still the consideration of power dissipation, since in this case we have current flow. So this is calculated as follows. We take the power dissipated, so it's the conductivity times the square of our electric field, and then it's times the volume of our device. So in this case, as we plug values in, we see that it's simply V squared over R. So hopefully this is very familiar to you from circuits class. So we see here we've started with Maxwell's equations and worked through these devices and coming up with the same equations we learned in circuit analysis. But this is, from an electromagnetic standpoint of view, this is the real reason why these equations are what they are and how the physical characteristics of the devices affect these values and how we get them. So finally, now we can use Ampere's law to examine the magnetic field between the plates. And when we do that, of course, we can plug in what we have for our electric field. And when we do magnetic field, just as the conductivity times the voltage over D times the Z value, where we're traveling on the Z axis. This results then in an inductance, which can be calculated either by calculating flux linkage or by accounting for the stored energy as follows. So we can calculate, anytime you have a resistance, there is some inherent inductance in the device. And so we can plug these values in, and we get these resultant equations. And so it's going to be 1/3 times the permeability times D times L, which is divided by W, which these are just the dimensions of our device. So you can see, if you know the dimensions and you know the physical characteristics, as in permittivity and permeability, you can work back to calculate what your inductance, resistance, and capacitance is going to be from these equations. So if we put all these things together, if we have this situation here where we have the conducting plates and then we have this imperfect dielectric in the middle, technically what we're going to have is all three, or the possibility for all three components to be present at one time. Because of the current flow, we will have some resistance. Because it will produce some magnetic field effects, we will have some inductance. And because we do have some dielectric effects in here, we will have a capacitive effect. So this is true. This is real life. Then, when you say you have a resistor, well, in reality, what you really have is an RLC circuit, but where the resistance part is much more dominant than the L and the C. When you get down into microcircuit design, where everything's on inside of a chip, that's not so clean cut anymore, because these other characteristics will start to they'll stay the same or may increase, but this is going to decrease greatly. And so now it's not so much that this is the dominant, you've got to take them all into effect, and it gets a little more tricky in that case. So just something to think about if that's one of the routes you're thinking about going. That's why electromagnetics is so important to understand that if you want to go into fields such as that.